거기에 그 메이크업 렉처라고 되어 있는 거는 다 출석이에요. 그거는 그걸 반드시 시청을 해야지만.
늦게 봐서 이렇게 글썼던 건가?
그렇죠. 아예 안 보셨거나. 늦게
시험 주자까지 포함이었어요.
그렇죠. 예. 뭐 근데 한 번은 제가 용서 봐드릴게요.
왜냐면 제가 지금까지 다 추석 때랑
네.
중간고사 때
언제 그 학생 성함이 어떻게 되시죠?
송준혁이요. 송준혁이요. 이거 중간고사 때 주간이거든요.
10월 22일하고
24일.
네. 결석한 게 없는데 이게 안 돼가지고 이름 적어놨었어요. 네네네. 성함이 김동규입니다. 네, 알겠습니다. 네.
이거 제가 저번에 복습을 잘못해가지고 이게 PMP, MPN이랑 이게 MPN짜리 식인데
네.
식이 똑같은데 그 이미터 커넥터가 좀 바뀌었잖아요, 위치가.
네.
근데 그거 반영해서 그 식을 똑같이 직관적으로 써주시면.
이게 스몰 시그널 모델을 그려보면
네.
MPN이랑 똑같아요.
아,
그렇기 때문에 똑같이 나와요.
네, 감사합니다.
이게 다 스몰 시그널 파라미터잖아요. R9이.
네.
네, 그렇기 때문에 똑같이 나왔어요. 이게 MPN이거든요. 똑같아요. 예. 네.
근데 그 제가 살짝 갑자기 기억이 안 나는데
네.
이렇게 보는 건데 그 R01.
네, 그 콜렉터를 보는 거죠.
네.
네, 그러니까요.
근데 그러면 그 여기에서 이게 R2면 이미터 쪽이 이거잖아요.
그렇죠, 예.
여기 R02가 있다고 생각합니다.
여기를 바라본 거죠. 여기 위를 바라본 거죠. 여기 위를 이렇게 바라봤을 때 그 RE가 요거라는 거예요. 네.
네.
네, 네, 감사합니다. All right. How are you doing? How are you doing? How come you look so sad? All right, let's get started. So, last time, what did we learn? We are trying to build a good current source, right? Good current source, right? Therefore, of course, the single transistor configuration serves as a what? Current source, but not good enough, right? Not good enough. So I try to introduce you what? Cascode stage to improve the transistor circuit configuration as good current source, right? So we stack two transistors in series so that we can make a better what? Current source, right? Better current source. So when you consider building a current source, what do you have to consider first? You gotta make the output impedance as high as possible, right? Right? That is what we did last time. All right? And we've learned about the short circuit transconductance. So the short circuit transconductance represents what? Represents what? Small change in voltage leads to large, not large, somehow large. Current change, right? Current change, right? Any circuit, any kinds of a circuit. Okay? So you see the clear difference between lowercase gm and capital GM, right? Right? And now, here we have a circuit with, what is this? I1, ideal current source. Okay? And here, this configuration, we can say this box as any circuit, not single transistor configurations. Okay? So let us determine short circuit transconductance, which is capital GM. Okay? So what do we have to do first? We gotta ground the output side as well as VCC, the common collector voltage. So what do we say about this grounding? AC ground, right? AC ground. And what do we do with I1 in small signal model? Yes. Open it, right? Open it. Make it open. Okay? Make open circuit. Right? In that case, what is happening? The circuit looks like this. Okay? Circuit looks like this. So this is simplified small signal model. Okay? Simplified small signal model. So you see that. What is this exactly? Single transistor transconductance, right? Since this I1 is gone, right? I1 current source is gone. That's why it is exactly looking like single transistor configuration. Therefore, the capital GM, which is short circuit transconductance, is exactly equal to GM1. Okay? GM1. All right? So now, if we calculate the voltage gain, which is capital GM times R out. In this case, what is R out? R out is impedance seen from the collector side, right? As I1 current source opens, right? So what is the R out? What is R out? R O1, right? R1, right? Therefore, the voltage gain is equal to negative GM1 times R1. So let us plug in the same value from the previous page. So R1 was 5K. So, which is negative 150. You look so happy. What is happening? What is so fun? Anyway, let's move. So here we have the voltage gain is only negative 150. Okay? Now. Here we have two different transistor configurations. So one is here, okay? And second is here. What is this? So if we add one more transistor in between current source and Q1 transistor, what do we say? Cascode stage, right? Cascode. Okay, cascode stage. So if we make the bottom side cascode stage, then let's see what is going to happen. Okay, so now here we see that the voltage gain is negative GM1 times R01, which was found from the previous page. So here, we calculated as negative 150, right? So here, the impedance seen from the collector side is called what? What is this? The impedance seen from the V outside. What do we say? R out, right? R out. What is R out? Since this is open, right? In small signal model, right? So, open circuit by definition, what is the impedance? Infinite, right? Then what is R out? R01 in parallel with R pi 2. Is that right? Am I correct? Oh, sorry. What am I talking about? So R out is R02 GM2 times R01 in parallel with R pi 2. Okay, please review the previous lectures. Okay, then the voltage gain becomes something like this. Okay, and now let us put some numbers. 5K, 0.03, 5K, 2.6K. Okay, then if we calculate this, then what we get here is 7,697. Isn't this amazing? By adding one more transistor, the gain has been improved by 50 times. Okay, 50 times. Isn't this amazing? Yes, I can see that. So, this is the powerful function of cascode stage, right? Cascode stage. So this is good, right? This is happening because we added this, what? Ideal current source. Okay, ideal current source. So let me ask you, is it possible to make ideal current source? No, it is impossible. Okay, so let us somehow replace I1, because I1 is never be possible in reality. Okay. With that in mind, so here the voltage gain, so this is second device configurations from the previous page, and this is simplified small signal model, and this is the detailed the gain calculations. Okay, since the first term is much greater than second term, we can just remove the second term so that we get this one, and the voltage gain is 7,697. Okay, from the previous page, and you can see the detailed calculations from P12. Okay, please review. Okay, please review. Now, I said adding what? Ideal current source is impossible. Okay, so let us replace the ideal current source with some other circuit configurations. Okay, so here, let us add a Q3 transistor here. PNP as non-ideal current source. I said transistor can be serving as a current source, right? But this is not ideal. Okay, this is not ideal. So here, what is R out in this case? R out is R up and R down. R in what? Yes? You said something? In parallel. Yes. Genius. Yes. R out is equal to R up in parallel with R down. Okay? So here, R out, so here, RO3 is R up. What is this? R down. Okay? They are in parallel. Okay? So now, let us plug in the same value here. Oh, not same value. What did I say about the output impedance of PNP compared to NPN? Which output impedance is higher between NPN and PNP in general? NPN. So let's say RO3, this is PNP R out, right? So let us say this is 4K instead of 5K. Okay? What about GM2? Still 0.03. RO2 is 5K. RO1 is 5K. RPi2 is 2.6K. If we calculate this, the gain is negative GM 1 R out. Okay? If we plug in these numbers, what you get here is negative 147. This is depressing, right? This is depressing. Why? Because compared to adding ideal current source, the gain has been degraded by 50 times by just adding non-ideal current source, which is PNP transistor, which is Q3 transistor here. Okay? So how can we improve this design? Again, we can use a cascade stage. Okay, so here, let us add one more transistor, which is Q4. So this configuration is cascade. Also, bottom side is also cascade. Okay, cascode 1 and 2. Okay, and now let us calculate the gain to see if this design improves the gain compared to the previous design. Okay, so what is R out here? R out here is again R up in parallel with R down, right? Okay, so here R up is this expression, and R down is this expression. Okay, so now let's say GM3 is 0.02. Why? Because PMP transconductance in general is lower than that of NPN, right? So let's say this is 0.02. And RO3 is 4K. And RO4 is also 4K. And R-Pi3, let's say 2.5K, whatever. Okay? And what about GM2? 0.03. 5K, 5K, 2.6K. Okay? So what you get here is 84 kiloohms. 84. What am I doing? 84 kiloohms. Okay? This is our out. Now, what is the gain? Gain is negative 2,520. Isn't this amazing? So compared to previous page, this one, how many times it has been improved? About 17 times? Let me calculate. Yes, that's about right. 17 times higher than previous one. Okay? So, this is more like ideal current source. Okay? That's why cascode stage is super duper powerful. Hey teacher, at this point, I was wondering something. What if you add more transistors in series? What is going to happen? You tell me. What is going to happen? It will behave like what? Ideal current source. Okay? But why? Why not? We are not adding more transistors. Why not? Why not? Because it consumes more powers and physically it is expanding. Okay? Okay? For the electronics, we gotta make it as small as possible, right? That's why we want to minimize the number of transistors. Okay, that's why just adding 2 transistors is enough for the current source. Okay, sounds good? Sounds good? All right, so here's the cascode stage. Here's the summary. Okay, so cascode stage actually boosts up the voltage gain and R out. And unlike RE, there is no headroom issue. What is RE? degeneration register. Okay? If we just use a transistor instead of degeneration register, we have no headroom issue because RE consumes some voltage, unlike the transistors. And what else? It can replace bulky RE. Okay, bulky RE. All right. So this is good. This is good. Cascode stage is powerful tool. Okay. So here's the attendance quiz. What is the answer? Tell me. What is it? F? You wanna get an F? F grade? Yes, F. You're a genius. Yes. All right. Now it's time to switch gear to another device, which is last device, MOSFET. Okay, are you excited? Before that, let us check the attendance first. Okay, I just want to see the electronic attendance really matches your presence. Okay. 이용성, 김교동, 배건욱, 전현빈, 이민정, 전지호, 최원준, 정성용, 신민송, 유이원, 로시디, yes, 장슈안유, 강승원, 광민경, 곽지성, 권도형. Don't raise your hand twice or 3 times, 4 times or whatever. Okay? 권동욱, 김경록, 김도원, 김동규, 김동주, 김민기, 김민석, 김민재. Where is he? Is he in Bayern Munich or something? Sorry about that. 김민준, 김민찬, 김사윤, 김서연, 김수호, 김승현, 김승우, 김시현, 김우진, 김진세, 김진우, 김현수, 김현탁, 나양수, 서지원, 유성진, 윤동수, 윤여건, 윤태호, 이동윤, 이정우, 이주형, 정규현, 정민재, 정병욱, 정재홍, 정지성, 차재준, 최원진, 최윤석, 최지운, 최지웅, 황주한, 강덕원, 김민서. Alright. I hope there is no discrepancy between electronic attendance and your presence. If there is, then what is going to happen? The students who have some discrepancy will lead to what? Please guess. Let me see. Okay, in the case, you can see me after the class. You can just write down here. Okay? Anyway, if there is a discrepancy between your electronic attendance and real presence, then what is going to happen? Please guess. You will face big consequences. What kind of consequences? I will consider this what? Discrepancy as what? The violation of academic honor code. Okay? What is going to happen if you violate the academic dishonesty in the US? Fail, right? Fail. Exactly what he said. Okay? Exactly what he said. So please inform your friends who violate this discrepancy, then they will have F grade. Okay, at the end of the semester. Sounds fair, right? Sounds fair. You guys are here, right? You guys are here. All right. Let's move on. So here, this is the last device, which is MOSFET. All right. So here's the outline. So the MOSFET is the final device you will learn from this class, and we will learn about the physics, voltage dependent resistor, comparison with the BJT, MOS capacitor, IDVDS equation, pinch-off and saturations. Okay, so please read chapter 6. Okay. So here I'm showing you the Apple's A13 Bionic chip, right? As of 2024, I believe there should be A16 Bionic chip, right? That contains more than 200 billion transistors, right? 200 billion transistors in this 1 centimeter square. Okay, isn't that amazing? So here, nowadays 7 nanometer architecture uses, okay? What is 7 nanometer represents? Which is the physical channel length dimensions, and which we will talk about in a minute. Okay, so this represents channel length. Of course, nowadays, the transistor channel is not two-dimensional. Okay? So traditionally, the transistor channel is two-dimensional. But now, FinFET or gate-all-around transistor utilize three-dimensional channels. Okay? But if we somehow those three-dimensional dimension as two-dimensional, nowadays we use 3 nanometers. Okay, 3 nanometers. And TSMC and Samsung are targeting 2 nanometer next year, right? Something like that, right? Right? And now, let us talk about Moore's law. What is Moore's law? So number of transistor is doubling every 2 years, same chip dimensions. Okay? So this principle holds for 5 decades. Okay? Isn't that amazing? Which is 50 years. Okay? 50 years. So nowadays, we are at gate-all-around technology or FinFET technologies. Okay? They are all three-dimensional MOSFET configurations. Okay? And as of now, there are like 100 billion transistors. Packed, 1 centimeter square. Okay? And now, let us talk about the comparison between BJT and MOSFET. So what are the advantages of using BJT over MOSFET? First, BJT makes better amplifier. Okay? In other words, GM for BJT is higher. Okay? Higher. Second, BJT shows predictable turn-on voltage, which is what? You tell me. Predictable turn-on voltage. What is it? You tell me. Anyone? For over 2 months, 1 month, right? You've learned about BJT, right? What is the turn-on voltage of BJT? Yes. I am so impressed. Even though this room is super duper hot, my body is all over with my goosebumps. So BVE is relatively constant. By the way, why this room is so hot? 700 to 800 millivolts, right? And what is the benefit of using BJT? Sorry. It shows large gain bandwidth. Okay? And fourth, it shows better performance at high frequency. Of course, GM is higher. You can expect that it shows higher gain. Okay, higher gain. And 6, it is operated in high power applications. And this is much more linear. And this is normally used analog circuit. Then, what is the benefits of using MOSFET over BJT? MOSFET is faster. Okay? Then we can utilize MOSFET as a better switch. Okay? And second, the MOSFET does not suffer from high device to device variations. And much easier to fabricate. Then, what can you say about the cost between BJT and MOSFET? Of course, MOSFET is much cheaper. Okay? And it shows less noise. And this is also, the fifth one is also the greatest benefit of using MOSFET. Can be made much smaller. In other words, what can we say? Anyone? You can express with a single word. What is it? It shows better what is it? Anyone? I can give you extra credit if you say that. Yes, density. I can give you 1 point extra credit. What is your name? Okay, that's good. Better scalability or density, whatever you want to say. But in the semiconducting industry, we normally use scalability. Okay, scalability. What else? It consumes less power. And it is normally utilized at the digital circuit. Okay? Sounds good, right? Sounds good. Now, yes. Are you good? That one? That's good. All right. Let's move on. So what is the MOSFET? What is the MOSFET? I said the words or tell us everything, right? So here, the M stands for metal, O stands for oxide, S stands for semiconductor. Okay? Semiconductor. And so let us divide 1 and 2. Okay? What is FET? Field effect transistor. Okay? So now, since you guys are 연세 genius, you can guess that the driven current of MOSFET is from what? Yes. The MOSFET current is driven by field effect. In other words, electric field. Okay, electric field. So unlike BJT, the source of current is from what? Electric field. Okay, in MOSFET. Okay, so if I ask you, what is the mechanism of current flow in MOSFET? What can you say? What can you say? What can you say? Yes. Drift current, or electric field, or field effect, whatever you want to say. Okay? So this is clearly not diffusion. Okay? The MOSFET current is driven by field effect or drift current. Okay? Then now, what about metal oxide semiconductor? If you imagine the structure of metal oxide semiconductor, you can imagine some device. What device? Conductor, insulator, and at the bottom there is a semiconductor. Let's say this semiconductor is doped. Then what can you say of this device? Metal, which is conductor, insulator, and at the bottom there is semiconductor, which is doped. Then we can say this is reasonable conductor, right? So what kind of device is this? Capacitor, yes. Juhan, great. Capacitor. So the MOSFET is actually capacitor. Okay? So if Samsung or NVIDIA recruiters ask you, what can you summarize? How can you summarize the MOSFET? You can say MOSFET is a capacitor. That's all. Okay? MOSFET is a capacitor. All right? So now, here's the actual MOSFET. Okay? So here, this is the cross-section image of MOSFET. What can you say? So here's source, and here's drain, and here's gate. Okay? With respect to gate, what can you say about this device in terms of geometry? Yes? Genius? Yes? BJT. That is a good guess. Where's? So with respect to gate, in geometrical view, what can you say about this device? So there is a source and drain. It are green colors. Right? What can you say about this? With respect to gate. Gate. unlike BJT, this device is perfectly symmetric. Symmetric. That's why MOSFET is easy to scale. Why? Because in BJT, collector and emitters dimensions are totally different. But here, the source and drain are exactly the same in terms of the dimensions. Okay? In that case, we can easy to interconnect between devices. Okay? So MOSFET is perfectly symmetric. But if you take a look at BJT, here's the emitter, here's collector. Is this symmetric? Not at all. Okay? Asymmetric. Which makes the BJT hard to interconnect. Okay? And the current flowing through the channels. Okay, we will talk about the channel in the later slide. Between the source and drain is controlled by gate voltage. Similar to BJT, we can say gate, we can say base, and source as collector, drain as emitter. Oh, sorry about that. It's a project. So this is emitter. This is collector. Okay? Very similar. Okay? This 3-terminal device. Okay, 3-terminal device. And we say N-channel MOSFET and P-channel MOSFETs. Okay, please guess. N-channel MOSFETs utilize electrons as carriers. Okay, what about P-channel MOSFET? Holes as majority carriers. Okay, so if we mix N-channel and P-channel MOSFET, then we say this integrated circuit as CMOS. What is CMOS? Complementary MOS. Okay, complementary MOS. Okay, and here we have one term which is called threshold voltage. Okay, if gate voltage is little over threshold voltage, the device conducts current. Okay, so here VG is less than V threshold, then ID, which is equal to 0. But if VG greater than VTH, enormous current flows through the transistor. Okay? And now let us take 5-minute break because we check the attendance, and then we can continue to talk about N-channel MOSFET.
혹시
네.
출석한 인원 중에서도 이름 안 부르신 경우가 있으신
네?
건가요? 출석한 인원 중에서도 이름을 아예 안 부르신 경우가 있으신 건가요?
출석한 인원이
그러니까 제 이름을 안 부르셨어요.
안 부르셨으면 여기다 적으시면 돼요.
여기 적으면
왜 근데 프린트가 안 됐나?
마지막 장이 안 된 거 아니에요?
아 그런 거 같네요. 마지막 장이 안 됐나?
그냥 여기 적으면 되나요?
네, 거기 적으시면 돼요.
엄청 많은데요?
맞네요. 이름 한 개씩만 적으세요.
이렇게 되면 된 거 아니에요?
아, 그거랑 맞는지 체크하려고.
아,
예를 들어서 학생이 이 학생 거 체크해주고 이 학생이 안 왔는데
아까 이름이 안 붙어가지고.
예, 그걸 지금 잡아내려고.
아,
과제 이게 이건 수업 혹시 끝나고 예. 네.
그 프로젝트 하는데요. 그 피스파이스 프로그램 있잖아요.
네.
옛날 거랑 좀 최신 거랑 저장하실 때 확천자가 다르거든요. 옛날 거는 그러니까 공지에는 SCH9로 배출하고 돼 있을 것 같아요. 근데 최신 거는 SCH8이 아니라 딴 걸로 오더라고요.
그 혹시 그 조교한테 질문해 보셨나요? 아니 조교한테 한번 하시겠어요? 예, 예. 네.
커렌트 소스 있다 치면 얘 저합차 있다고 해서 이거
네. 그거는 아이디어. 있을 수가 있죠. 있을 수가
저희가 예를 들어서
예, 있을 수가 있죠.
A, B, C라고
근데 보시면은 이게 있어도 상관이 없는 게 이 커런 소스 때문에 얘는 전류도 흐르게 돼 있죠. 그러니까 얘가 얘의 전류를 강제하는 거죠. 강제하는 역할을 하기 때문에 여기 전압차가 발생해도 얘의 오퍼레이션에는 전혀 상관이 없어요.
이게 전압차가 발생해서
네.
그러니까
예.
이제 한다.
네.
예를 들어서 따로 치면
네.
사실 저희가 이 영어로
어떤 식으로 영어로 해요? 예.
근데 그렇게 생각해 이게 그럼 여기 전류가 있나라는 생각을
아, 왜냐면 이 전류차, 이 전압차를 B, C, 그 B, E를 보는 거기 때문에 여기가 0이어도 상관없어요.
네. 그러니까 제가 여기 이렇게 보니까 어차피 여기랑 여기랑 똑같은 노드라고 치면
아, 예, 예.
안 흐르는 거라고 보니까
아니요, 전류 흐르죠.
네, 전류가
왜냐면 여기에 바이아스를 걸리면은 전류가
VC 아니
예,
이렇게
그렇죠.
걸릴까요?
예, 감사합니다.
학생증을 두고 와서
아, 네,
찍진
네,
않고
네.
통영 출석은
여기에
위에서 좀
네. Here's so hot, right? Compared to Minnesota. So when are you leaving?
22nd December.
I'm leaving as well. I'm leaving Korea. At the end of this year, I will go to US. Yeah, for a year.
For a year?
Yeah.
You want to be teaching too?
For my sabbatical year.
So that?
Yeah.
So research.
Yeah. I'm going to Georgia Tech next year. If I get a chance, I may visit you. If I get a chance, I might visit to Minnesota.
Might visit Georgia too.
Sure.
It's a family.
Okay. Always welcome.
Have you been to Georgia?
Yeah. Oh, I think twice. Yeah. It's hot over there.
Maybe I like it more than Minnesota.
Okay. All right. Let's move on. So here I'm showing you the N-channel MOSFET structure. Okay. So here, if you take a look at this schematic image carefully, then you see the structure of MOSFET. Here we have source and drain as N plus doped silicon. Okay, normally the doping concentrations for this N plus is like 10 to the 16 to 10 to the 18 in cubic centimeters. Okay, and there is a substrate which is P minus substrate. What is P minus? What does P minus mean? It's lightly doped, right? Lightly doped. Lightly doped with P-type dopant, such as boron, right? Such as boron. So concentration is like 10 to the 12 to 10 to the 13. Okay. And there is a insulator, okay, bridged between source and drain. Okay, insulator. So here, as an insulator, SiO2 is the most famous one. Okay, back in the 1970s and 80s, people used SiO2. Nowadays, for this dielectric, people use something so-called high K dielectrics. Okay, high K dielectrics. I will tell you why we use high K dielectric. Okay, such as hafnium oxide, or aluminum oxide, or something like that. okay, which shows high electrical permittivity. Okay, electrical permittivity. Okay, and you will see why we use high K dielectric. And here's the symbol, circuit symbol for MOSFET. Okay, so as you see this, immediately, what can you see? What can you see? You have two shields, right? What is this? Two shields. What is this? Capacitor. Yes. Capacitor. Okay. So what does this arrow stands for? Yes? Yes, yes, yes. Current flow directions, right? Okay, current flow directions. Okay. So now, let me ask you. What can you say? What can you say? When you apply DC to the capacitor, then do we have current flow in the capacitor? No, no current flow, right? So if we apply VG, then there is no current flow. Okay? Then, what can you say about the beta for MOSFET? Infinite! Yes, here. The beta is equal, sorry about that. So here has to be IG, okay, IG, okay, the gate current, okay. So beta here, similar to BJT, ID. So this current is called ID. So source to drain, there is current flow. We say that's ID, which is drain current, okay. So beta in this case is ID over IG. What is the value? Infinite. Okay? Infinite. So in MOSFET, you don't have to consider beta at all. Okay? In that case, what's happening? What's happening?